Now we finish Chapter 5, beginning with the section entitled Stats on page 102 of the book. Now, a stat is a statistical transformation, and it transforms the data according to your command automatically, typically by summarizing it in some manner. We've seen this stat, the smoother, which calculates a smooth line, a smooth mean of y conditional on x. Here are some other stats and what they result in. Stat bin results in the geome bar is used with the geome bar, geome freak poly, and geome histogram. Stat bin 2D, we've seen that one for the geome bin 2D. Stat bin dot for the geome dot plot, I don't believe we've seen that. Stat bin hex for the geome hex, we saw some hex applications. Stat box plot produces the geome or transforms data in the geome box plot. Stat contour transforms data in the geome contour. Stat quantile, which breaks it up into quantiles, or usually 4 quarters for geome quantile. Stat smooth, we saw that for geome smooth, and stat sum for a geome count. Now let's talk a little bit about generated variables. So stat produces generated variables. A stat will take a data frame as input and it returns the data frame as output, adding new variables to the original data set. And these new variables are what are used in those respective geomes that apply to each of the stat transformations. It is also possible to map aesthetics to these new variables. For example, stat bin, the statistic that counts in bins for histograms and for other plots, produces at least 3 variables. Count, where it counts the number of observations in each bin. Density, which is the frequency of observations in each bin. Sometimes it's related to count, but it can also be used to normalize. Density is the percentage of total observations in a bin divided by the bar width. And X, which is the center of the bin. You can use these generated variables instead of the original variables present in the data set. For example, the default histogram geome assigns the heights of bars to the number of observations. We've seen that. But if you'd prefer to use a more traditional histogram, you can use the density. Okay, so what's the difference between the two? Well, in this first plot, there is no difference. This first plot, this is a histogram of price with a bin width of 500, and it uses count. And you can see count here on the y variable. Okay, and so keep in mind what these bars look like. And so now we're going to use density, which is the percentage in the bin divided by the width of the bin. And in this particular case, since we're using price, the relative proportions are going to be the exact same. So the bars look the exact same, but notice here on the y, now we have a measure of density. But again, if we flip back and forth, there's no change to the plot because we did just one variable, price. But it becomes useful, density versus the count becomes useful when you want to compare the distribution of multiple groups that have different sizes. For example, let's take a look comparing the distribution of price within cut. So here we do a geome freak poly using count for price within cut, and we're going to color the cuts by group. Okay, and so the ideal in this case has many more in absolute numbers and counts. The ideal has many more that are diamonds that are priced around $2,000. But these relative heights do not reflect proportion of these different groups because there are different numbers of total diamonds within each of these 5 cuts. So now, if we use density instead of count, it normalizes or makes them all equivalent in terms of their base in calculating the proportion, not the absolute count. And so now you see that some of the lesser quality cuts, ideal is the best, fair is the worst, increase in density at this price of around 2,000, but moreover, at higher prices, it almost appears that some of the lesser quality, inferior cuts have a higher price. For example, we can see that the premium is above the ideal over here, and in fact, very good is above ideal in some places, which doesn't make a whole lot of sense, but that is, it seems like low quality diamonds to be more expensive on average. Okay, let's talk about position adjustments. Position adjustments just apply minor tweaks to the position of elements within a layer. 3 common adjustments are position stack, where you stack overlapping bars on top of each other or areas on top of each other. Fill, where you again stack overlapping bars, but the top is always at 1. And dodge, where the bars or box plots are side by side. So let's take a look. Here we just set up the plotting frame. So it's blank. Okay, so here we're going to call geobar, which by default uses position stack. And the areas are the relative amounts within each of these colors down here for these cuts of the stones. So you can see that the ideal cut seems to take up more area in most of these bins for colors. That is, there's more ideal cuts than there are premium or very good or good or fair. But if we use fill instead, it sets the top to 1 and uses the proportions. So now you can compare with line of sight. You can just go across and you can see, again, the ideal does seem to take up more of the relative proportions of each of these colors, except maybe perhaps color J. But you can readily compare right across how much each particular cut, what proportion that comprises within all of the diamonds in each of these different color bins. And then we have position dodge, which takes the 5 bars, the 5 cuts within each color and places them side by side. And again, ideal does outstrip each of the other cuts within each of the particular colors. There's also a position adjustment for identity, but let's not get hung up on it. It doesn't do anything. It's not useful for bars because the bars cover the ones that are behind them. But it can be useful in, for example, the frequency polygon. In that now you can see the absolute numbers of each one. And, for example, comparing color and cut, if you want to see the absolute number count within each one, the identity argument for position is useful. Okay, finally, 3 position adjustments used mostly for points. And what they do, they're used for overplotting with points. You can nudge points that moves them a little bit to a fixed offset. You can jitter them. We've seen that with adds a little random noise to every position. Or you can jitter dodge them, which dodges the points within groups and then adds a little random noise. But rather than looking at each one of these, let's just look at jitter. All 3 of these do the exact same thing. Note, though, let's do the first one. So we're plotting displacement by the highway mileage for MPG, and there's a lot of those. So we're just going to use G on point, and we're going to say position jitter, and it just randomly shuffles the points around just a little bit, so the ones that are lying on top of each other might not be so occluded. But note it's a random shuffle, so every time I execute the same command, the plots move in their direction just ever so slightly, in their position ever so slightly. The overall pattern and trend is the same, but the individual points move just a little bit around. Well, you can write that same plot like this. You can just say geom point, but the position is geom jitter, but this time we're specifying the width and the height of the jitter. So it moves at 0.05 and it moves at the height 0.5. So it's not necessarily random in this case, but again, it's going to move it is random because it moves it in those directions in a random way. And so every time I do it, again, the pattern is the same, but the points are in slightly different positions. Or we could do that, write that same plot just like this. It does the same thing. And you can see as I execute it several times, the points move around ever so slightly, but the pattern remains the same. Okay, well that's the end of chapter 5. Next in class we'll begin chapter 6, which I believe will take us 2 days.